Once upon a time, a long, long time ago, in a cave somewhere, there was some cave person who first started studying numbers. And then the cave person had an idea. The idea is functions. Instead of just studying numbers, this cave person is going to study numbers depending on other numbers, the relationships between numbers. There's another way to think about functions. A different metaphor is that functions eat numbers, and after they're done processing them, they spit out some other number. Functions eat numbers and spit out numbers, but the food chain keeps going. The derivative is an operator, and what that means is that it's like a function for functions. The derivative eats a function, and after it's done with it, it spits out a new function. The derivative. First we studied numbers. Then we studied functions, which are numbers that depend on numbers, or things that you do to numbers. And now the derivative. The derivative eats something, which itself eats something and spits out numbers, and then the derivative spits out a new thing that eats numbers and spits out numbers. So the derivative takes a function and gives you a new function. And this ddx notation is so powerful that you can start to talk about the derivative even before you've applied it to any function. Look at this. This is some sort of equation, but it's really a nonsense equation. The second derivative minus 1, what does it even mean? Equals the derivative minus 1. What am I doing here? Multiplying? Who knows? The derivative plus 1? This sort of nonsense looks similar to something very reasonable, that x squared minus 1 is x minus 1 times x plus 1. There's actually some sense to this. So let's try to make sense of the right-hand side after I apply it to a function. So we don't even really know what this means, but the notation's so powerful that it's just going to lead us forward. So I'm going to copy down ddx minus 1 in parentheses, and I have to figure out how I'm going to apply this thing to f. I'm going to act like this distributes. So I'll write ddx of f plus 1 times f. Now I can keep on going, right? This, if you kind of imagine, might distribute over this. What would that mean? I'm going to ddx this whole thing. So ddx of f plus f minus 1 times this. So minus ddx of f plus f. And now I can keep calculating. The derivative of f plus f, well, the derivative of a sum is the sum of the derivatives, so that makes sense. That's the derivative of f plus the derivative of f minus the derivative of f minus f. I'm subtracting, summing f, so it's subtracting f. Now good news, I've got a plus derivative here and a minus derivative of f there, so what I'm left with is ddx of f, which I could write as the second derivative of f minus f. Well, I could also write this as the second derivative minus 1 applied to f. And that's exactly what's on the other side of this equation. At this point, this is all a sort of cheating. So if this doesn't speak to you, don't worry. The upshot, though, is that differentiation is an operation that you apply to functions, and it's possible to reason precisely about differentiation in the abstract, just as an operation.